So hello everyone. In lesson 2, I'm going to show you how to do ground state electron configuration. And what it is, it's a shortcut way of representing the electron filling of an element. And the reason it's short is because you don't have to draw the energy level diagrams. You can represent the order in one line. So first of all, what you'll notice is with electron configuration, it's going to be in this general format here. So the number in front is your whole number coefficient. That's going to be the n number, so that's going to be the period that the atom falls in. The P is the orbital block on your periodic table, so that's going to be either an S, P, D, or F. And the number up here, your exponent, represents the electrons within that orbital block. And there's two ways you can write electron configuration. One is longhand, and longhand is where you're going to start over here with hydrogen and work across your periodic table, just like with your electron filling. And then the shorthand is where you're going to find your nearest preceding noble gas. So the noble gas that comes before your element, start there and then do your configuration. Okay, so I'll show you 3 examples here. The first one is magnesium. So if we look at where magnesium is on the periodic table and we do an energy level diagram, we're going to start here with hydrogen and we're going to go across and stop at magnesium. So what we're going to have here is a 1s with 2 electrons, a 2s with 2 electrons, a 2p, which will be full with 6 electrons, and then your 3s is going to have 2 electrons. So remember your filling rules. Hydrogen is a 1s with 1, and then helium is 2. You go to the next row, lithium, beryllium, and then your p block, and then magnesium ends in your third s block. So that's what it looks like. So the longhand is just taking this and writing it out in this configuration. So we're going to start with a 1s with 2 electrons. So the 2, the exponent is the number of electrons. A 2s with 2 electrons. A 2p with 6 electrons. And then the 3s with 2 electrons. So that's your longhand. So this is just a shortcut version of this. Okay. For the shorthand configuration, if magnesium is here, your nearest preceding noble gas, you go backwards, is going to be neon. So we represent that with a square bracket around it. So we're starting with the electron configuration of neon, which ends at the 2p6. And then you're going to add the 3s squared, and that's the shorthand electron configuration. So remember, this here is just 1s squared, 2s squared, 2p6. That's what that is. So instead of writing that out, we write it as neon. The second one we're going to look at is the oxide ion. So oxygen is over here. So if we draw our energy level diagram, we'll have a 1s with 2 electrons, a 2s with 2 electrons, and then a 2p going across your 2p, 1, 2, 3, 4. So we'll put in our orbitals, 1, 2, 3, 4. Now, because we want the oxide ion, we know that oxide forms an O2 minus charge, so we're going to add 1 electron here and 1 electron here. So the longhand configuration, we're going to do 1s with 2, 2s with 2, and a 2p with 4. So that's what oxygen looks like. But to get the oxide ion, we're going to add 2 more. So that becomes a 6. So what we get now is 1s squared, 2s squared, 2p6. Shorthand configuration. So if we look at oxygen and we go backwards to the nearest preceding gas, you'll see that it's helium. So we're going to put He here, and then we'll do our 2s squared 2p4. And then we're going to add 2 to that. So we cross out the 4, we add 2, it now becomes a 6. And what you're going to notice now is the 2p6, which is here, is now neon. So this becomes neon. So O2 negative is isoelectronic with neon. So when you have an ion that you make and it ends at a noble gas and you're writing the shorthand configuration, then that noble gas that you've just turned it into becomes the proper way to write it. So we wouldn't leave oxide like this, we would write it like this. The last one is vanadium, and I chose that because that was in one of your D blocks. So vanadium, we're going to have a 1s with 2 electrons, a 2s with 2 electrons, a 2p is full. And then after the 2p, so remember, after your 2p is full, you now go to your 3s, and then you're going to fill your 3p. And then you're going to go to your 4s, and then remember, this jumps down a shell. This is your third shell now, but it's a D, and we're going to go across 1, 2, 3. Okay, so we have our 3s with 2, our 3p will be full with 6, and then you're going to do a 4s will be full, and then your 3d, your 5 orbitals, you're only going to have 1, 2, 3 electrons. So you can see how spacious, how much space that takes up. So longhand, we're going to have a 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d3. So that's your longhand. Now shorthand, go to vanadium, find it on your table, go backwards, and your nearest preceding noble gas is argon. So we're going to put argon here, and argon we know ends at the 3p6, so this here is your argon. And then we add in the 4s squared 3d3. So your shorthand, as it says, is even shorter than what your longhand is. Okay, so let's go and do some practice. Okay, so the first element we're going to look at is nitrogen. So you locate nitrogen on your periodic table, is in period 2, and it's in the P block. So you know it's going to end with a 2p something, and when you count over 1, 2, 3, it should end with a 2p3. So what we're going to have for nitrogen, 1s squared, 2s squared, 2p3. Okay, and that's your electron configuration for nitrogen, as simple as that. Sc is over here. It's the first electron in the 3d block, so we're going to go to the 3d block. So 1s squared, 2s squared, 2p6, 3s squared, 3p6, 4s squared, and then a 3d1. And there's your energy level diagram for Sc. Fluoride ion, F is here, so fluoride ion negative, we're going to add one more electron, so we're going to turn F into Ne. So longhand, starting at the beginning, we'll have 1s squared, 2s squared, 2p6, 3s squared. Sorry, let me just reach over here. I went too far here, just erase that. So this becomes 2p5. That's what fluorine looks like here. And what we're going to do is we're going to add one more and turn this into a 6. And that becomes, you'll notice shorthand, that is going to become neon, because the fluoride ion and neon are isoelectronic. Aluminum, the same thing. Aluminum's a 1s squared, 2s squared, 2p6, 3s squared, and then a 3p1. So when you look at aluminum here, you'll have your 3s with 2 and a 3p with 1. Now we want the cation, so to do that we have to get rid of this entire shell here. And again, what you'll notice is this becomes neon. So these two here are sorry, my cat's on the table. Isoelectronic. Okay. All right, so let's get into some more complex ones here. So Ga. So Ga on your periodic table is way down here, number 31. And what we're going to do is let's just start, instead of doing the whole thing, let's just start with argon, so the shorthand. So we're going to have argon here when we go to the nearest preceding, and then you're going to do a 4s squared, a 3d10, and then you're going to go to a 4p1. So we're going to have a 4s squared, 3d10, 4p1. So gallium has two oxidation states. Here's why. You always have to look at your highest shell. So for example, if we were to draw this, 4s with 2, 3d, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and then a 4p with 1. That's what you have. So remember your removal rules. So to make this a cation, the first thing you're going to do is remove these two. That gives you a +1 charge. And then you can remove these two, and that gives you a +3 charge in total, because now you've lost 3 electrons. So you're going to show the same thing over here. So you're going to lose this, that becomes your +1, and then you're going to lose this, and that becomes your +3. So in the end, you have 2 oxidation states, and they are Ga plus and Ga3+. So if you're asked to show oxidation states, which you would be, you can either do it this way to show what it is that you get rid of, or write it out like this, and can't always go to your highest end value, the P's first, then the S's, if you have the D's in between. Notice with aluminum up here, there's no D in between. So you can't lose the P's, just this P, and get a +1 charge, because it doesn't exist for aluminum. You have to get rid of the entire shell. Here, because of the D's in between, and because of the stability of those D's, you can lose just this and have just a +1 charge, or you can also lose these and have a total of a +3 charge. So that's how you get those 2 oxidation states. Okay, so the last thing we'll do is, this is how you would see it on a test or a quiz that I would give you, is this idea here. So this is really important that you go through and do this practice. So first of all, we're starting up here with X. So X just means a mystery atom or ion. So first of all, you notice there's no charge on this one, but this one has a charge. So here we're looking for a 2+ ion. Here we're looking for a neutral atom. So the nice thing with the atoms is you just follow the order and look at where it ends. So this atom ends at a 4s squared. So you go over here, 4s squared is calcium, because it's in period 4, and it's the second electron in the S. So this here is just calcium. This one's a 2+ charge, so that means you lost 2 electrons. So we need to figure out where that is. Well, when you go through the 3p6, after the 3p6, you are supposed to go to a 4s squared, then the D's. Well, you're going to notice that in here, your 4s squared is removed. It's missing from this configuration. So those are the 2 electrons that were removed. So if you were to plop those back in and then go to your 3d8, so 1, 2, 3, 4, 5, 6, 7, 8, this is nickel that lost 2 electrons, because you always remove from the highest end value. This one here is strictly an atom. There's no charge, so you don't have to worry about all of this. Just assume it's done correctly unless you're told there's an error in here. And you can go all the way to the end. You don't even need any of this. And you are ending at a 6p4. So there's period 6. There's the p's, 1, 2, 3, 4. And your element is polonium. Now this one here, we want the lead 4 plus charge, and you know on your periodic table lead has 2 charges, a 2 plus and a 4 plus. So what we're going to do here is, starting at the beginning with hydrogen, let's write out the longhand configuration. So 1s squared, 2s squared, 2p is full with 6. Then you go to the 3s full with 2, 3p full with 6, 4s squared, and then you jump down to a 3d 10, and then after your 3d you're going back up into the 4p, and it is full, and then after your 4p you do a 5s, and then after your 5s you're back into a d's, but if this was a 3, this is a 4, so this is a 4d10, 5p 6, and then after 5p6, you're going to go to 6s squared. Now remember, after the 6s, you have to jump down into the 4f block. So we're going to have a full 4f14 filled. Come out of the f block back into the d's, and this is now a 5d because it's one less than the n value, so a 5d10, and then your 6p. And your 6p you're going to put in, where's lead here, 1, 2. So it's a 6p squared. So we want the 2 plus charge. Do we get rid of the 6s squared or the 6p first? Well, the answer is you have to get rid of the p first, because a p in N6 is higher energy than the s. So you're going to ignore the 4f and the 5d because your highest n value is here and here. So if we get rid of those, we now have the 2 plus charge. So that's just the 2 plus, but we want the 4 plus. So now you're going to get rid of these 2 next, and those gone will give you your 4 plus charge. So you don't have to rewrite any of this. You can leave it like that and just show that getting rid of these gives you a 2 plus, getting rid of those in addition to these gives you a total of the 4 plus, which is the charge that we want. Okay. The last one here means a -1 means we've added an electron. So where do you add an electron? To your highest energy orbit. Well, there's your 5th shell. You have an S and a P. So the S would have been filled before the P. So that means the extra one we added. So what we did here is we added an electron, which means this was 5p5 before we added. So 1, 2, 3, 4, 5. This is your P block. 5. P5 is iodine. So we took iodine, we added one more electron to it and turned it into xenon. So this is I negative. So when you're doing a negative ion, go backwards. Okay, in that if we had 6, if we are given 6, we added 1, so that means we have to go back 1, so that when we add 1, it takes us back up to the 6. Now these ones here, we want the shorthand configuration. So find dB on your table, and you'll notice that dB is number 105. So our nearest preceding noble gas going backwards is Rn. So we're going to put Rn here, and then after Rn we have a 7s and it's full. So where do we go after the 7s? We go into the second F block. So if this is a 4F, this is a 5F. So we're going to have 5F14. And then we have to go back into the D, so 3, 4, 5, 6. So this is a 6D block, and we only go over 1, 2, 3. So we're going to have a 6D3, and that's your shorthand configuration for dB. Okay, chloride ion. So Cl is up here. So the nearest preceding noble gas is neon, so we're going to put Ne here. And then after Ne, we have a 3s squared, 3p 5. So remember, always do the atom first, and then what we're going to do now is we're going to add one. So if we added one here, if we add an electron here, this becomes 6. So now we've gone from chloride, so adding one more turns it into argon. So the chloride ion is isoelectronic with argon, and this would be how you would write the shorthand configuration in the end, because it actually becomes a noble gas. Re, so Re, where is Re on the table? Oh, number 75. So going backwards, your nearest preceding noble gas is Xe. And then after Xe, you're going to have a 6s squared. And then remember, after your 6s, you have to go into the 4f. And we're going to fill it with 14. And then we go back up into the 5d block. So block 3, 4, 5, and 1, 2, 3, 4, 5. We're going to go over 5 electrons, and there's your configuration for Re. Aluminum, the nearest preceding noble gas for aluminum is neon. And then after neon, we have a 3s squared, 3p1. And what we want, though, is the 3 plus ion. So we're going to take all of this away. We have to take both the P and the S because there's no D block in between, and aluminum can't have two charges, only one fixed charge of +3. So as you can see, all you have left is neon. So this just becomes neon in the end. And you don't have to rewrite it, you've got it there. Okay, the lead 2 plus. So PB, our nearest preceding noble gas is Xe. And then after Xe, we do a 6s squared. And then we jump down into the 4f block and fill it to 14. And then after the 4f, we go back into the 5d and it's filled. And then a 6p, and in the 6p, lead is the second one over. So if we want the 2 plus, we've already done this up here. We're just going to get rid of this here. And that's all you need to do. You don't need to rewrite it. If you wanted the 4 plus, you'd get rid of this and this. So there's your 2 plus charge. Iron 2 plus. So iron is here in the 3d block. So the nearest preceding noble gas is argon. So we're going to do AR, and then we're going to have a 4s squared and a 3d, and we're going to count over 1, 2, 3, 4, 5, 6. And we're going to get rid of the 4s squared because that's the highest n value, and that gives us our 2 plus. Okay. ZR. So ZR is in period 5. So our nearest preceding gas, our noble gas, sorry, to ZR is Kr. So we're going to put Kr here, and then after Kr, we're going to have a 5s squared, and then we're going to have a 4d, and you'll see on your table, it's the second one over in the 4d, so 4d squared. And that's it for that one because we don't want an ion. But if we wanted an ion for this one, we'd have to get rid of the 5s squared first, and then we can get rid of each of the individual electrons in the D. And we'll do one of those shortly. Okay, X negative 2, and it's just Kr. So if you go to Kr on your table, X negative 2 means we added 2. So this means here that we added 2 electrons to the original atom. So we go backwards, 1, 2. So the original atom was Se. We added 1, 2 electrons to it, and it became krypton. X2 plus, so we're going to start with argon. And then we have a 3d5. Well, again, looking at your table, after argon, we should be going to the 4s before the 3d. So that tells us that we are missing the 4s squared in here. And because this is a 2 plus, there are no other electrons missing. So we can now go to our 3d and count over 5. 1, 2, 3, 4, 5. And our ion is Mn. And we lost 2 electrons to give it a 2 plus charge. This one here, X 5 plus, so this means we lost 5 electrons. So we're going to start at Kr. So Kr is here, and then it goes to the 4d10. Well, you'll notice after Kr, the 5s is missing. So we know that the 5s squared has been removed, but that only accounts for 2 electrons. We need to account for 5. Well, the d block is full with 10. So what comes after the 4d is going to be your 5p. So this block in here. So what we're missing from in here is the 5p with 3 of them, because the 3 missing from the P and the 2 from the S gives you your 5. So when you go over to the 5p, 1, 2, 3, the atom we started with was antimony, and then we got rid of the 5p3 first, so we got rid of these 3 electrons first to get a 3 plus charge, and then we got rid of the 2 electrons in the S to give us a total of a plus 5 charge. Okay, so these ones here were removed. Bi is a 3 plus, so Bi is here. The nearest preceding gas is Xe. So we're going to have Xe here, and then after Xe we do a 6s squared, and then you're down into the 4f block, and it's full. And when you come out of that, if this was a 6s, you're now in a 5d, and it is also full. And then Bi is in period 6 in the p block, so this is a 6p, and it's 1, 2, 3 over. So to get the 3 plus charge, we always take away the p's before the s's, so we're going to get rid of these, and that gives us the 3 plus charge that we want. And you should also notice that bismuth can also have a 5 plus charge, because we can get rid of these and get the 5 plus charge from that. But this is all that it's asking for. So Mn, the last one here, so Mn is in the 3d block, so the nearest preceding gas is Ar. And after Ar, we should have a 4s squared, and then a 3d, and we're going to count over 1, 2, 3, 4, 5. So it's a 3d 5. So if we want the 5 plus charge, remember, you can't take away this 3d 5 and think that that's correct. You have to remove from the highest energy level first. You have to remove the 4s squared first. So that gives you a 2 plus. So if you want the 5 plus, these electrons here are 5 singles, so you would lose them 1 at a time. So now you're going to lose 3, so this becomes 2, and that gives us the 5 plus charge that we want. So we're going to lose 3 electrons from the D, 1 at a time. Okay, and you can see that because if you drew the 4s with 2 and the 3d with 5, you can actually see that this is where you would lose your 2 plus, and then you could lose these 1 at a time. So 3 plus, 4 plus, 5 plus, and then carry on 6 plus and 7 plus. Okay, so on your sheet, there is on the last page, there's a little bit of a summary, and then there's some practice questions that I've given you, and you can work through those, and the answer keys are provided for you. If you have any questions, just please send me an email. All right, thanks.